All right, today we are diving into the absolutely incredible world of a material that could, and I mean could, completely change how we heal. We're talking about something called nano-hydroxyapatite and its potential to help us, well, build the perfect bone. Let's get right into it.
I mean, really, have you ever stopped to think about it? If you break a bone or need a new joint, what do doctors actually use? They can't just use any old material. They need something the body doesn't just tolerate, but actually welcomes, something it can work with to heal itself. And that very question, right there, is what drives this entire field of medical science. So, to figure out the best way to fix a bone, scientists did the logical thing. They looked at bone itself. And you know what? They found the perfect blueprint hiding in plain sight.
Okay, meet hydroxyapatite, or HA for short. This stuff makes up a whopping 70% of our bones. It's basically nature's own ceramic, and it's what gives our skeleton all its strength. And the best part? Since it's already a part of us, our body doesn't freak out when it sees it. It's biocompatible, which just means our tissues get along with it, and it's bioactive, meaning it actually does positive things when it's in there.
Think of it like a construction scaffold, but for your cells. When an implant coated in this hydroxyapatite is put into your body, it sends a signal to your bone cells like, hey, over here, this is a great place to build. They grow right onto it, weaving into it, creating this incredibly strong natural bond. This whole process is called osseointegration, and it is absolutely crucial for any implant to be successful.
So, hydroxyapatite is pretty great, but what if we could make it even better? I mean, what if we could give it actual superpowers? Well, that's exactly what happens when you shrink it way, way down to the nanoscale.
On the left, you've got your standard microscale HA, pretty small. But on the right, that's nano-hydroxyapatite, or NHA. By shrinking these particles down to a size that's almost hard to imagine, we totally transform its properties. It's the exact same chemical, sure, but it starts behaving in a completely new and much more powerful way.
And these new powers are a total game changer. I mean, look at this list. That massive increase in surface area. That means way more room for your cells to grab on and start growing. This nano version is stronger, it blends in with your body better, it actually calms down inflammation, and, get this, it actively encourages your bone-building cells to get to work. It's incredible.
So here we have it, this wonder material that seems absolutely perfect for fixing bones. But, like any good story, our hero has a flaw, a big one, a critical vulnerability that holds it back from its true potential.
Just when it feels like we found the ultimate solution, the perfect key to bone regeneration, we hit a wall. A really big one.
Brittleness. That is the Achilles heel of pure nano-hydroxyapatite. In its raw form as a pure ceramic, it's kind of like fine china. It can handle being squeezed really well, but if you pull on it or hit it, it can just shatter.
And this is the deal breaker. While NHA is fantastic for things like coatings or filling in small defects, you couldn't make an entire hip replacement out of it. Not yet, anyway. It just doesn't have the toughness to handle the stresses of daily life like our natural bones do. This mechanical weakness, this is the single biggest puzzle scientists have to solve.
So this challenge kicked off a huge quest. If the raw material itself is a bit brittle, maybe the way we make it matters. Scientists started coming up with different recipes or synthesis methods, each one trying to cook up a stronger, better version of NHA. Let's take a look at the three main contenders.
Okay, first up, we've got a method that sounds really complicated, but the idea is actually pretty simple. Imagine carefully mixing two totally clear liquids together and boof, a solid, cloudy material forms right out of thin air. That's the basic idea. Now, this recipe is super popular because it's easy, it's cheap, and it's incredibly green. The only thing left over is water. You also get really good control over how big the nanoparticles are. The major downside, though, the tiny particles love to stick together in clumps, which can make the final material a little less effective than it could be.
Our second recipe is called the sol-gel method. Now this one is for the perfectionists. It's a much more precise technique, and it's famous for creating materials that are incredibly uniform, all at nice, low temperatures.
Yeah, the huge win for sol-gel is control. Because it's a low-temperature process, it doesn't cost a lot in energy, and it produces this exceptionally pure, super consistent NHA. That makes it absolutely perfect for creating those thin, bioactive coatings on medical implants we were talking about earlier.
And our final recipe is the hydrothermal method. Honestly, the best way to picture this one is to think of a scientific pressure cooker. Seriously.
By cranking up the temperature and the pressure inside a sealed container, this method can churn out really pure, perfectly formed NHA crystals, and it does it fast. What's even cooler is that this method lets scientists create all these unique shapes, like tiny nanowires or nanotubes, which just opens up a whole new world of possibilities for how we can use this stuff.
And here's the ultimate showdown. This table just lays it all out, right? You can see that wet chemical is cheap and simple, but the purity is just okay. Sol-Gel is also low cost, but with high purity, making it a fantastic all-around choice. Hydrothermal is a bit pricier and more complex, but look what you get. High purity, high speed, and what the source calls very high potential for doping. And that right there is the key to everything.
So after looking at the material itself, its big weakness, and all the different ways to make it, where do we stand? What does the future actually look like for building better bones?
The single most important thing to take away from all this is that there is no one best recipe. There's no silver bullet. The method you choose depends completely on what you're trying to do. If you need a ton of powder cheaply, maybe you use wet chemical. If you need a flawless, thin coating for a titanium hip, Sol-Gel is your winner. The future is all about customizing the material for the specific medical problem you're trying to solve.
But what about that core problem, the brittleness? Well, this brings us to the next great frontier, something called ionic doping. The best analogy is making steel. You start with plain old iron, but then you add just a tiny bit of carbon, and suddenly it's dramatically stronger. Scientists are doing the exact same thing here, adding tiny amounts of helpful ions like magnesium or zinc right into the NHA structure to finally beat that brittleness and boost its bioactivity even more.
And that leaves us with one last really fascinating question. If we can pick the perfect recipe and then dope it with just the right combination of ions, are we finally, after all this work, on the verge of creating a synthetic material that isn't just like bone, but is in every important way its equal? Or maybe, just maybe, even better? The quest for sure continues.